Welcome to a visual exploration of continuum mechanics for piping engineers, mediating the load, the physics of stress, strain, and material limits. Every deformation is a dynamic conversation between an applied load and the material's internal architecture. Stress is the invisible internal resistance measured across a cut plane. Normal stress involves pulling or pushing, while shear stress involves sliding or twisting tangentially across the internal face. Strain is the dimensionless geometric consequence of internal stress. Axial strain is the fractional change in length, and shear strain is the change in internal angle, measured in radians. Young's modulus, E, translates internal stress into physical strain. It is the proportionality constant in the linear limit, as defined by Hooke's law, E equals sigma over epsilon. Poisson's ratio, nu, governs the three-dimensional preservation of volume. It is defined as the negative ratio of lateral strain to longitudinal strain. The elastic trinity mathematically binds isotropic materials together. Knowing any two of these constants allows a stress engineer to perfectly define the total elastic behavior of the material. The stress-strain journey shows the material's timeline to its breaking point, moving from the elastic region through the yield point, strain hardening, and finally necking and fracture. In reality, true stress never decreases. Our engineering assumptions do. Engineering stress uses the original cross-section, while true stress uses the instantaneous cross-section. Material personas differentiate between ductile resilience and brittle suddenness. Ductile materials show massive plastic deformation and visible warning signs before failure, unlike brittle materials. The piping engineer's reality is a continuous, bidirectional feedback loop where primary loads cause strain and secondary loads, like thermal expansion, cause stress. Mastering the elastic constants is key to design. This concludes our video on piping design simplified.